Hello, in today's lesson we are going to continue looking at Equilibria. We are going to have a look at lesson 2 today, which is changing temperature and pressure. So our learning intention is exactly the same as last lesson. We've already gained an understanding, hopefully, of what is meant by dynamic equilibrium, but we're going to investigate the other two factors which can affect the position of equilibrium and hopefully be able to explain these in detail. So the second experiment, we've done the concentration experiment last lesson. Aim is to investigate the effect of changing pressure has on the position of equilibrium. And here you'll see we have two gas syringes, and one of them has increased pressure, one of them has decreased pressure. Remember, all we mean by increasing pressure is we mean squashing the available size. So when the plunger is pushed all the way in, we are increasing the pressure in this space. When we pull it all the way out, we are decreasing the pressure in this space. So here is the equilibrium equation. We have N2O4 on the left, which is yellow, and on the right we have nitrogen dioxide, which is brown. So the starting colour is a pale yellow. When the plunger is pushed all the way in, that increases pressure, and as we can see from before, it turns yellow in colour when we do that. When we pull the plunger all the way out, that decreases pressure and the gas turns brown in colour. So from that kind of little experiment, if you will, we have realised that when you increase pressure, the equilibrium will move to this side, which is the left, and it shows the yellow colour. When we decrease pressure, the equilibrium is moved to the right, which is our nitrogen dioxide, and that is the brown colour we're seeing. Why does this actually happen? Well, if we have a wee look at our results table, if we increase pressure and it turns yellow, that tells us it's moving towards the reactants. Why this happens is when we increase pressure, the equilibrium will move to the side of the equation with the least number of moles of gas. If we have a look at the equation, we only have 1 mole of dinitrogen tetraoxide, and on the other side we have 2 moles of nitrogen dioxide. So if we increase pressure, we're moving to the side with the least number of moles of gas. But if we decrease pressure, then we get a shift to the right, which is the most number of moles of gas. So why this happens, or a kind of straightforward, simple understanding of why this happens, is when you increase pressure, you are limiting the available space there is for molecules to move around. So it's going to favour the side that has the least number of moles of gas, or the least kind of number of molecules that are moving around, and squashes them closer together. So it's going to be beneficial if you are getting squashed together, that there are less molecules in that space. Decreasing pressure is just the opposite. Decreasing pressure is increasing the available space for the molecules. So it gives them more space. So that favours the side of the reaction that has more number of moles of gas, or more molecules of gas taking up the space. Some important points to note about pressure is that pressure only affects equilibrium of a system which involves gases. So if you see an equilibrium that has a mixture of liquids and gases, and you are looking at how pressure might affect that equilibrium, then you have to ignore any substance that is a liquid. It doesn't count when you're counting the number of moles, it's only gases. A pressure change will only alter the equilibrium position if there are different numbers of moles of gases on each side. If you have 2 moles of gases on one side and 2 moles of gas on the other side, and you increase or decrease the pressure, nothing will happen to the position of equilibrium. It will stay exactly where it is. So here is an example question that you may be asked. In which of the following would an increase in pressure result in the equilibrium position being moved to the left? So what you need to say to yourself, right, an increase in pressure, we are squashing the available space into a smaller volume. So that's going to favour the side of the reaction with the least number of moles of gas. So in which of the following would an increase in pressure result in the equilibrium position being moved to the left? So we are going to look for an equation where there are less number of moles of gas on the left than there is on the right. That happens to be C. As we can see, we have 4 moles of gas on the left in A and only 2 on the right, so that's not good. We have 2 moles of gas on the left for B and 2 on the right, so that's not going to be affected at all by an increase in pressure. C, we have 2 moles of gas on the left and we have 4 on the right, so that is the one where we have the least number of moles on the left-hand side. And the one at the bottom as well, we have 3 moles of gas on the left and 3 on the right, so that's the same. It's not affected by equilibrium. Changing the temperature then. So how does temperature affect the position of equilibrium? Again, these are experiments that if we were in class we would be carrying out. The nitrogen dioxide one with the gases is just a demonstration, but hopefully if we're able to get back into the classroom then we can show you some of these. This one is an experiment that you could very well do on your own. You start off with a solution which is kind of purpley bluey in colour, and if you, as the instructions suggest, cool down the bottom of the test tube by placing ice on it and heat up the top of the test tube, probably with a Bunsen burner and not one of these, you end up with this lovely kind of gradient colour here where it's pink at the bottom and blue at the top. So here is the equilibrium equation. And as we can see, this reaction is delta H positive, so it's an endothermic reaction. So that means that the forward reaction, so it going from here to here, is an endothermic reaction. That means, remember, that the backwards reaction must be exothermic. So what happens when we decrease the temperature then? If we have a look at our diagram, when we decreased the temperature, and this was adding the ice to the bottom of the test tube, it went pink. So turning pink is going to be moving the equilibrium towards the reactants. As we can see, this is a pink colour here. And increasing the temperature, so heating that up with a Bunsen burner at the top, will end up being a blue colour. So blue colour is moving towards the product side. Now, why does this happen? Just like anything else, when you change something in the system, the equilibrium will try and reverse that change and counteract it in any way it can. So if you decrease the temperature, it will try and make more heat energy to increase its own temperature. A reaction which makes its own heat temperature or heat or gives off heat is an exothermic reaction. So if the forward reaction is endothermic, the reverse reaction is exothermic. So when you decrease the temperature in this reaction, it turns pink and moves to the left because it's trying to increase its temperature by being an exothermic reaction and releasing heat. The opposite is true for increasing the temperature. If you increase the temperature, the reaction is going to try and then decrease the temperature by moving in the endothermic reaction, which uses up heat energy. So decreasing temperature moves towards the exothermic reaction. Increasing temperature moves towards the endothermic reaction. In this scenario, our forward reaction is endothermic and the reverse is exothermic. So decreasing the temperature moves it towards the reactants and increasing the temperature moves towards the products. This is the little conclusion, kind of what we've just said, but I'll read through it again so that you can copy it down if you're doing that right now. So increasing temperature favours the endothermic reaction. The system tries to reverse the added heat, meaning it favours a direction which uses heat energy rather than producing it. So that makes sense. Decreasing the temperature is going to favour the exothermic reaction. The system is going to try and create more heat energy to replace the energy which was lost when we decrease the temperature. An example question of this would be here. Under the conditions used industrially, ethane and steam react as follows. So you've got the equation here, and as you can see, this time the forward reaction is delta H negative, which is an exothermic reaction. Now, if you see a delta H at the side of your reaction, that always represents the change in enthalpy for the forward reaction. So you just need to flip it for the reverse. And it says, which set of conditions would give the best yield of ethanol at equilibrium? This is one of the reasons that we study equilibrium, is to gain the most product we possibly can. So we are going to be able to manipulate a system to make sure that we are getting the most product out that we can. So we're given some options here, and we are going to have to combine our knowledge of pressure and temperature and how both of those affect the equilibrium. So first of all, since it's kind of fresh in our mind, if this reaction here, which in the forward reaction is an exothermic reaction, that's the reaction we are wanting to happen because that's producing our ethanol. If it is an exothermic reaction, then lowering the temperature is going to be the best, because then the system is going to push the equilibrium in the direction of the exothermic reaction, and that's going to produce us more product. Remember, the reason it does that is when you decrease the temperature, it will try and increase the temperature, and the exothermic reaction is going to produce more heat energy. So a low temperature is going to be more beneficial than a high temperature. So immediately we can rule out A and B, and we are going to be going between C and D. Now we have to look at the pressure situation. So on the left, we have 1 mole of ethane and 1 mole of water, both in the gaseous state. And on the right-hand side, we have 1 mole of ethanol gas. So remember, increasing the temperature pushes the equilibrium to the side with the least number of moles of gas. That is what we are looking for here. Our least number of moles of gas happen to be on the right-hand side, and that produces the product, which is ethanol, that we want in this reaction. So the answer to this question is C, which is low temperature and high pressure. The last section of this is catalysts. What effect does adding a catalyst have on the position of equilibrium? Now, we know that catalysts can be used to speed up reactions, and reactions can be carried out at lower temperatures using a catalyst. But adding a catalyst to a reaction at equilibrium doesn't actually affect the position at all. All it does is it allows equilibrium to be reached more quickly or established at a lower temperature, which makes reactions more profitable. Here are some questions. We, as usual, will talk through the question, and then if you want to pause, give the question a wee go, and then unpause, and we'll go through the answers. So question 1, the following equilibrium exists in bromine water. So you have bromine and water, which is a red colour, forming bromide ions, hydrogen ions, and you have OBr negative here as well, which are both colourless. And the question asks, the red colour of the bromine water would fade on adding a few drops of a concentrated solution of, and you have 4 different options. If we add HCl to this, we are going to be adding hydrogen ions, which is going to be increasing the concentration of a product. We don't want that because that will mean our equilibrium will shift to the left, and that will give us more of a red colour. The same would be happening with B, because we'd be adding bromide ions, and they would be moving the equilibrium to the left again, producing more of a red colour. The exact same would happen with D here, because we have Na plus and OBr negative. Again, we're adding more of the products, which will produce more reactants. That leaves the answer to be C, which is silver nitrate. And this is one of the more tricky examples in equilibrium, because what is going to happen here is the silver is going to react with the bromide ion to form silver bromide. And if you look that up in your data booklet, it is insoluble. So what's happening here is a precipitation reaction where these are coming together, reacting together to form silver bromide. And if something is insoluble and the rest of your equilibrium is in solution, then that substance will no longer take part in the equilibrium. So what this is basically doing is pulling the bromide ions out of the equilibrium, which is decreasing the concentration of the reactants, and therefore the equilibrium will try and make more products by getting rid of this red colour, shifting the equilibrium to the right, where we will have more colourless compounds. So that is the only option out of those four that will allow the red colour to disappear. That is a tricky example, and if you didn't know that, then simply by eliminating A, B and D, you can still get the answer. Question 2. A catalyst is added to a reaction at equilibrium. Which of the following does not apply? So we have A, B, C and D. A, the rate of the forward reaction increases. That's true. B, the rate of the reverse reaction increases. That's also true. C, the position of equilibrium remains unchanged. Yep, that's true. So the answer must be D. The position of equilibrium shifts to the right. We should know that adding a catalyst does not affect the position of equilibrium, so it cannot possibly move to the right. That's why the answer is D. Number 3, when chromate ions dissolve in water, the following equilibrium is established. So you have chromate ions, hydrogen ions, and then dichromate and water on the right-hand side. We have yellow colour on the left and orange on the right. The question asks us to explain fully, so it's worth 2 marks, the colour change that would be observed when solid sodium hydroxide is added to the solution. So what's going to happen then if we add sodium hydroxide? Well, sodium hydroxide is an alkali and we have some hydrogen ions here. So what's going to happen is the hydroxide ions are going to react with the hydrogen ions and effectively pull them out of the equilibrium. So they're reacting together. There's going to be less of these hydrogen ions on the reactant side. What the equilibrium is going to do then is it's going to push it to the side which will make more of these to replace what was lost. So it's going to shift the equilibrium to the side of the reactants or the left side, and therefore a yellow colour will be observed. Now, if you said all of that and that the hydroxide ions will react with the hydrogen ions and pull them out and it'll move to the left, you'll only get 1 out of 2. It says explain fully the colour change, so you must say something about the colour of the equilibrium to get the second mark. Question 4. The following equilibrium involves 2 compounds of phosphorus. An increase in temperature moves the above equilibrium to the left. What does that indicate about the enthalpy change for the forward reaction? So if you are increasing the temperature and it moves the equilibrium to the left, we know that an increase in temperature favours the endothermic reaction. So if the reverse reaction is endothermic, then that must mean that the forward reaction is exothermic. Number 2, how would increasing the pressure affect the position of equilibrium in this reaction? Well, we have 3 gases and 1 solid, so let's ignore the solid. And let's count the number of moles of gases on each side. So we have 4 moles of gases on the left and 3 moles on the right. So if we increase the pressure, remember this will move the equilibrium to the side of the reaction with the fewest number of moles of gas. In this scenario, that is the right-hand side or the product side. Last one, number 5. What would happen to the equilibrium position in the following reaction if the temperature was increased? So increasing the temperature, remember, favours the endothermic reaction. As we can see, this reaction is exothermic, so it's going to shift to the left or the reactant side because of that. And that's only worth 1 mark, so that's all you have to say. So hopefully after these 2 lessons you have a good understanding of what dynamic equilibrium is, and you can identify 3 different factors which can affect the position of equilibrium. Hopefully you can also use your understanding of the experiments that we have had a wee look at to explain why this happens in detail.